In this video, we are finally getting to some partial differential equations. This is covering the very beginning of chapter 4 in the Solution Techniques for Elementary Partial Differential Equations, second edition by Christian Constanda. Earlier, we went through the material in chapters 2 and 3. Not all of this, we skipped some of these sections at the end here in chapter 3. But both chapters 2 and 3 deal with content that's very closely related to solving partial differential equations, but doesn't actually feature solving a differential equation at all. Sturm-Liouville problems, for example, happen to be boundary value problems dealing with second order ordinary differential equations. But these techniques are critical for solving some partial differential equations. Now, chapter 4 deals with these three equations: the heat equation, the Laplace equation, and the wave equation. In this video, we'll look at the derivation of the heat equation and the corresponding initial and boundary conditions that actually make sense for this. And in other videos, we'll talk about the Laplace equation and the wave equation. But I want you to see sort of what's coming. If you go through this text in chapters 5 and 7, we will learn methods for solving these equations. So we'll apply the method of separation of variables to homogeneous equations, and we'll look at the wave equation, the heat equation, and Laplace equation. And then we'll look at eigenfunction expansion in chapter 7. And then in chapter 10, we'll use the method of Green's functions to look at those. And then in chapter 11, finally, we'll say the heat equation, wave equation, and Laplace equation are very special forms of those linear second order partial differential equations. In 11, we say, well, what if we generalize that a little bit? What if we're not dealing with an equation that is the heat equation or the wave equation or the Laplace equation exactly, but it's a more general hyperbolic equation or a more general parabolic equation? We'll talk about that when we get to the material in chapter 11. So that's what's coming. But first, we're going to focus on mathematical modeling in general, and then the focus of this video will be the derivation of the heat equation, our first mathematical model from chapter 4. So let's talk about mathematical modeling. And mathematical modeling is a process, and it basically involves 3 steps. The first thing that we do is we write that mathematical model. For our purposes, it will consist of a partial differential equation and initial conditions or boundary conditions or both. And that will be based on usually some assumptions from physics and also our observations of some physical phenomenon. So we'll say that the model will be written in terms of mathematical expressions describing the quantitative relationships between the physical quantities involved. Now, I actually really love this. I love analogies too for describing physical relationships, but when I'm really interested in how something actually works, I'm not looking for an analogy. I want like a description, something that tells me like how the physics evolves. And differential equations and partial differential equations don't require you to use some analogy. They actually describe those relationships with functions, and I really love that. Oops, sorry, there's some weirdness going on with my video here. So we are, sorry about that, describing the quantitative relationships between the physical quantities involved. Alrighty. Now, after we have that mathematical model, we solve the mathematical model. Seems pretty straightforward. You create a well-posed problem that describes the physical conditions, that describes how things evolve and behave and are related to each other, and then you solve the equations. And of course, we're going to use whatever methods we're familiar with. Oops, not variable, various. So we'll say the equations are solved by means of various mathematical methods. Basically, the methods that we study when we study partial differential equations. Just for example, when we're discussing these models. And then finally, after you have stated the model, solved it, now you've got some function that's representing some physical quantity. We want to interpret the mathematical results there. So that function is going to tell us something about the physics involved. So the mathematical results will be interpreted from a physical point of view. Basically, we're going to step away from the math and then focus on the physics and see if the solution to that mathematical model, which consists usually of a differential equation in either some initial conditions or boundary conditions or both. We're going to look at that solution and see if that actually makes sense for whatever it is we're trying to describe. If it doesn't make sense, we might go back to our mathematical model and include more terms, include terms that would better physically describe, or better describe, excuse me, the physics of what's happening there. Or maybe the model was originally too difficult to solve and we had to eliminate some terms to simplify it in order so that we could solve it. So there are lots of possibilities here, but I think that this is pretty straightforward. You just describe the physics with equations, you solve the equations, and then you interpret those and you say, does this actually physically make sense? Now, in this chapter, we're going to deal with three types of mathematical models. We're going to derive all three. In this video, we're going to start with the heat equation. And then after that, we'll talk about the Laplace equation. And then finally, we'll discuss the wave equation. Now, not all partial differential equations are one of these, the heat equation, the Laplace equation, and the wave equation. But each of these is a representative of an entire class of linear second order partial differential equations. For example, the heat equation is the simplest form of what we call a parabolic equation. So once we solve that heat equation as our first example of a parabolic equation, we can think about generalizing that again later when we get to chapter 11 of the PDE textbook. So that's the plan. And just as a reminder, a partial differential equation so I will abbreviate PDE, we have been abbreviating PDE, is just an equation that contains an unknown function And that unknown function is a function of several variables. And one or more of its partial derivatives. It's like an algebra class, you're trying to find x, got an equation involving x, trying to find x. In a differential equations class, trying to find y, or you're trying to find that function, that unknown function in the equation. The difference between a partial differential equation and an ordinary differential equation is that in a partial differential equation, the function that we're looking for depends on more than one independent variable. So the derivatives aren't ordinary derivatives, but partial derivatives. Okay. So now let's talk about the heat equation. Oops. Specifically, we'll be talking about heat conduction in a one-dimensional rod. Okay, so let's say we've got a heat conducting rod. In the shape of a thin cylinder. And it's described by the following physical parameters. L is its length. A is its cross-sectional area. And we'll assume that that's constant. And if we want to, when we draw this rod, we can draw it on what we think of as the x-axis. We can label x equals 0, one endpoint of the rod. X equals L would be the other endpoint of the rod. And so it might look something like this. And I'll put a y-axis here, but it's really not important. We're just focused on this one dimension. The length of the rod is L. This cross-sectional area right here, that's A, and that's just a constant. And E of X and T is the heat energy density. This is heat energy per unit volume. Gotta keep going. There are a lot more physical parameters to describe. And we want this function to represent the heat flux. Now this is heat energy per unit area. Flowing to the right, that's our assumption. And that is arbitrary, it's just a convention, but we have to stick with that convention. We're gonna say that that's the positive direction for heat flux to the right. And this heat flux is heat energy per unit area flowing to the right per unit time. And Q of X and T will represent heat sources or sinks. This is also measured in heat energy per unit volume this time. And this is generated inside the rod or lost inside the rod. per unit time. Now, typically when you read a partial differential equations book, instead of saying sources or sinks every time, they're just going to use sources whenever they talk about Q of X and T. And they're not going to specify sources or sinks, but obviously if it's negative, then it's a sink. If it's positive, then it's a source. Okay, so those are our physical parameters. And there are some assumptions that we're making. One of the assumptions is that this lateral cylindrical surface of the rod is insulated. So there's no heat exchange across this part in the middle. So you're not losing any heat or gaining any heat across this boundary that goes around the outside. And again, just as I mentioned a second ago, sources will be taken to mean either sources or sinks. Either one is fine. Now, when we come up with the partial differential equation, it will be derived based on the law of conservation of heat and energy. That is our last and probably most important assumption. We assume that this law of conservation of heat energy is actually true. Turns out that it is. And it says this, excuse me, the rate of change of the heat energy in some body is equal to the heat flow across the boundary per unit time plus the heat generated or lost by sources or sinks per unit time. We'll just say that it's generated by sources for simplicity. And I think that makes sense. This is saying the time rate of change, and it's implied that that's a time rate of change of the heat energy in a body. Just depends on the heat flow going across the boundary per unit time, plus any heat generated by the sources. It's sort of a rate in, rate out thing. You're just adding heat flow across the boundary plus any heat flow or any heat that is lost or gained by sources. So I think it's pretty intuitive. But given all of these physical parameters we've discussed, it's going to lead to a partial differential equation that we can solve. Simple, simple. Okay, so let's talk about an arbitrary length of this rod between x equals a and x equals b. So at x equals a, we might be over here. And at x equals b, we might be over here. And we're talking about this piece in between x equals a and x equals b. Focused on that, let's look at this differential equation, or let's look at this, law of heat, conservation of heat energy, and translate it into a differential equation. this says the time rate of change of the heat energy in a body. So that's the derivative with respect to time of what we want is the total heat energy in the body. Now, E of X and T is heat energy density. That's heat energy per unit volume. And this is a function of both X and T. So it's a function of position in the rod, and it's also a function of time. If we integrate that from X equals A to X equals B, this is heat energy per unit volume. If I multiply by a tiny volume increment, which would be that area times dx, that's going to give me the total heat energy in the body between X equals A and X equals B. And that's going to be a function of time. We're taking the derivative of that with respect to time. And that's just this left-hand side here of, it's a statement, but I've written it almost as an equation. This is the time rate of change of the heat energy in a body. It's right here. And let's write all of these. Let's describe all of these pieces. Okay, heat energy per unit volume. This is just a tiny volume increment. Or it's an infinitesimal volume increment. Let's say it's not. Say that we're still dealing with delta X. It's that area times delta X is giving us the volume of that little slice. So we're taking heat energy per unit volume, multiplying by volume. We're getting a total heat energy between X equals A and X equals B. Again, that's right here inside our rod. And we're saying the derivative of that with respect to time is equal to, what does the law of conservation of heat energy say? Heat flow across the boundary per unit time. Now, heat flow across the boundary per unit time deals with this heat flux. Now, at X equals A, we'll know the heat flux is given by this function evaluated at X equals A and T. And then on this side, and that's going to be going in, because remember, we're measuring heat flux is always flowing to the right. Then on this side, we would have a heat flux given by this function of T at this little boundary here. At X equals B, we would have this function of T representing the heat flux going to the right. But we're actually interested in the part that's going inside. So we're going to multiply that by -1 and say that if we multiply by -1, it's actually going to go to the left. So that will give us heat flow across the boundary. And that's per unit area. So I want that flux going in on the left, and then the flux going in on the right, and then we add them together. On the right, we're assuming that's negative because of our convention that the heat flux always goes to the right. And this is heat energy per unit area. We're going to multiply by area. Times the area of our little slice there. Okay, so that's the heat flow across the boundary per unit time. This is heat energy per unit area. I should also say per unit time. So that when I multiply these, I get the areas cancel and we get heat energy per unit time over here. Okay, so that's this piece. We took care of that side, and we're going to take care of that side. Now over here, we want to add the heat generated by sources per unit time. Now, the heat sources or sinks are denoted by this Q of X and T. This is heat energy per unit volume generated or lost inside the rod per unit time. We want to add all of those sources or sinks. We want to add all of those up for that interval between X equals A and X equals B. And this is heat energy per unit volume. So we want to multiply by a volume increment. So we'll have heat energy per unit volume per unit time times volume is going to give us heat energy per unit time. And then we're adding all of those together. So this deals with our sources or sinks. And that's it. That's the translation of the law of conservation of heat energy. Now, we don't like to keep it in this form. We're trying to derive a single equation. We've got all these integrals everywhere. There's a lot going on here. We're going to simplify this a lot before we continue. But I just want you to see that this is the time rate of change of the heat energy in a body. And over here, we're saying that that's equal to the heat flux, or the heat flow across the boundary per unit time, plus any heat generated by sources per unit time. So those are the three terms described in our law of conservation of heat energy. Now let's see if we can't make this prettier. I want to make it as simple as possible. And hopefully, as we simplify it, it will be more insightful for us. Now, this expression over here, we can think of as the result of an integral. You guys remember from your Calculus 1 class, I'm sure, that if you take the integral from x equals a to x equals b of f of x, if you want to find that value, you would typically find the antiderivative, plug in a, plug in b, and subtract. So you would have that right there. That is very similar to what we have here. Now, ignore the t for right now, but look at the spatial dimension. X is starting at a and going to b, and here I've got f of b minus f of a. So this is like -1 times the result of some evaluation of a definite integral. So we can replace this with the following. And the left-hand side I'll leave exactly the same. On the right, this can be replaced with the integral from a to b of -1 times the partial derivative of this function with respect to x. Because if we're taking the antiderivative of the partial derivative of this function with respect to x, what we would get is that function evaluated at b and a, and then we subtract, and then I multiply by -1 so that we get that expression evaluated at a first minus the expression evaluated at b instead of the other way around. So we've got that there. And then over here, we also have this. Okay, now I've got integrals everywhere. And remember, a is just a constant, and that constant factor is multiplying every term in this equation, so we could divide it out. And this partial derivative, or this ordinary derivative with respect to t of this function of t, we can bring that inside. Write that this way. So dividing out the a, you get this. And I can write all of that as a single equation if I wanted to, all within a single integrand, because I'm integrating this from x equals a to x equals b, and the same here and the same here. And so we can write it this way. If I add this to both sides and subtract this from both sides, we'll have this. Oops, minus. And that will be true for t greater than 0. And it's also true for any a and b. Remember where we started. Oops. Over here. It's something that looks like this. If it's true for any a and b, it doesn't matter which x value we just choose to start or which x value where we choose to stop. If that doesn't matter at all, then that must mean that the integrand is 0 all the time. So we have this integrand equals 0 for x between 0 and L and t greater than 0. Or typically it's written like this. We've got the partial derivative of that heat energy function, that heat energy density function with respect to time, equals the negative heat flux with respect to x plus this source term, Q of x and t. Now, what's good about this is that it's a partial differential equation. But what's bad about this is that I've got three functions here. I've got a heat energy density function and a flux function and a source function. Now, maybe we know the nature of the sources and we can just fill that in. But we might want to express this differently. Might want to write everything in terms of a temperature function, and we'll call that temperature function U of x and t. In order to do that, we need an alternate way to represent this expression and an alternate way to express this expression, and we'll do that using a couple more assumptions from physics. So we're almost there, but not quite there. This is equation 4.1 in the text, and we're going to keep going. We want to describe this in terms of temperature. So here's a notation that is pretty standard. U of x and t is going to give us the temperature in that rod at position x in the rod for x between 0 and L and at time t. Now C is a function of x, and that's going to be the specific heat of the rod. This is the heat energy that raises the temperature of 1 unit of mass of that rod by 1 unit of temperature. And we assume that this is independent of the temperature. Just to make everything simple. Kappa sub 0 of x is what is known as the thermal conductivity. We'll also assume that this is independent of the temperature. And I'll just say temp independent for simplicity in my notes. And rho of x, this is the mass density. This is traditional density, mass per unit volume. And I think Dr. Constanda probably specifies mass density as opposed to weight density. So we're not dealing with pounds per cubic foot, for example. It's probably kilograms per meter cubed or something like that. Okay. Then the total heat energy in the rod, which can be represented this way. Remember what all the pieces represent again. This is heat energy per unit volume. This is a volume increment. When I multiply those and integrate, I'm getting the total heat energy in the rod between x equals A and x equals B. When I do that, or when I express it that way, it turns out it can also be expressed this way. The total heat energy in the rod between x equals A and x equals B is also the integral from A to B of the specific heat times the density times the temperature times the volume. And the volume is that area times dx. Okay, so let's do a little dimensional analysis and make sure we've got the right units here. This is specific heat. This is heat energy to raise the temperature of 1 unit of mass by 1 unit, and that's of course of temperature. And this is mass density, so mass per unit volume. This is actually temperature at location X within the rod at time t. And here's our volume increment again. And again, this is just for that part that we're interested in between x equals A and x equals B. But it's true for all t greater than 0. And I claim that this is an alternate representation of this total heat energy in the rod between x equals A and x equals B. Let's make sure the dimensions work out. So this says, or this quantity is specific heat. So it's heat energy, and it's energy necessary to raise the temperature of 1 unit of mass by 1 unit. So it's energy per unit mass per unit temperature. Okay, and then we're going to take that and we're going to multiply by our traditional density, which is mass per unit volume. And then we're going to take that and we're going to multiply by temperature. And then we're going to multiply by volume. Hopefully when we're done, we actually get what we have over here. And I think we do. The mass reduces, the volume reduces, the temperature reduces, and what we're left with is energy. And that's exactly what we were expecting to get. So this right-hand side is an alternate representation of the total heat energy in the rod between x equals A and x equals B. But x equals A and x equals B could be any values between 0 and L. If A and B are arbitrary, then we're going to have that this is equal to this all the time. And of course, A is just a constant, so we could divide it out. So we must have this. So E of x and t, that's our heat energy density, is equal to that specific heat times the density function, that's a rho, not a p, even though I just made it look like a p, times the temperature. So that heat energy density can be written in terms of temperature in this way, for x between 0 and L and for t greater than 0. And if you're saying to yourself, why is that important? Because our goal is to write this as a differential equation that describes the temperature of the rod at a particular position at a particular time. So now I know how to represent this expression in terms of temperature, which is represented by that U. Now there's another law according to Fourier's law of heat conduction. We have the following. This heat flux, heat energy per unit area per unit time, is equal to -1 times that thermal conductivity times the change in the temperature function with respect to x. So it's dealing with that change in temperature in the x direction as our spatial variable changes, while that temperature, or excuse me, while that time t is held constant. This is heat energy per unit area per unit time, and we're using that convention that the positive direction is to the right. Oops, I lost my H in that thermal conductivity. There we go. Okay, so now our heat flux can be written in terms of temperature. And that's nice, because that means we can substitute this in terms of temperature. We can substitute this in terms of temperature, the temperature of the rod itself. The sources and sinks would not be a function of the temperature of the rod. We would think of that as, these are external sources and sinks. So we wouldn't expect that to depend on our function U. But now that we've got this in terms of the temperature function and this in terms of the temperature function, we can substitute those in and come up with a partial differential equation that discusses the temperature of the rod at a particular position x in the rod and at a particular time t. So it's really just a substitution. It's not that advanced. But it's nice. It's nice to know where all of that comes from. So we had this differential equation. From before, just from the law of conservation of heat energy. And now we're going to replace this E of x and t with this function. Now, I want you to notice that the only function here that depends on t is the temperature function. This is a function of position only. The density is a function of position only. We're assuming that that density is not changing with time, and neither is the specific heat, which I think makes physical sense. So when we take the partial derivative of that expression with respect to time, you guys have had Calc 3. This is treated as a constant. This is treated as a constant. And we take the derivative of this with respect to time, treating x as a constant. Okay, so that's what we have there. And that's from this equation. Now we also know that the heat flux is given by this -1 times this thermal conductivity times the excuse me, partial derivative of the temperature function. Whoops. Sorry about that. The partial derivative of the temperature function with respect to our spatial variable, where our time is held constant. So we can substitute that in right here. and you're taking the derivative of that, or partial derivative of that with respect to x. And of course, these qualifiers, they should come down here as well. Of course, the negative times the negative is a positive, and we get this. Now, if we make a couple of additional assumptions, this differential equation simplifies quite a bit. If we assume that that rod is uniform, which means that that specific heat, the density, and the thermal conductivity are all constants. So we're assuming that. And if we also assume at the same time that there are no sources, that means Q is equal to 0. Well, then this is a constant, this is a constant, and this is a constant. And if that's a constant, when I take the partial derivative of this partial derivative with respect to x, that becomes a second partial derivative with respect to x. So what we have is this, c times rho times the partial derivative of u with respect to t equals this thermal conductivity times the second partial derivative of u with respect to x. And q is 0. And this is true for x between 0 and L and for t greater than 0. And if you want to, you can take this kappa sub 0 divided by that specific heat times the density, and you can sort of group them all together into one constant. Dividing by that and then calling that new constant k, we have this. And this is the typical form of the homogeneous heat equation. This says that the temperature in the rod with respect to time, the time rate of change of that temperature, holding our position in the rod constant, is actually equal to some constant times the second partial derivative of that temperature with respect to the spatial variable. I think that's pretty cool. I love equations because they really do tell you a lot about how things actually work. Like this is how the temperature dissipates, or how heat changes. Pretty nice. And of course, as I said, K is just that kappa naught divided by C times rho. That's a constant, and we call that the thermal diffusivity of the rod. Now, if there are sources, then we could represent the partial differential equation this way. Just add a term for the sources. Now, this Q of x and t is not the same as this Q of x and t, because if I divide both sides of this differential equation by c times rho, where c and rho are constants, we're going to have a 1 over c times rho times this source function. This source function already includes that 1 over c times rho. So if you want to, you could call this function Q star we'll say where our new function representing the sources is equal to 1 over c times rho times the original source function. So it's just a constant multiple of the source function that we had before. Okay, so that's the heat equation. That's probably the most important part of our mathematical model, describing the temperature of that rod. But if we want to describe that temperature, if we want to find U of X and T, we're going to need more information. Since we've got a partial derivative here of U with respect to time, we're going to need one initial condition for time. Since we have a partial derivative of our temperature function with respect to X twice, got two derivatives there. We're going to need two what we call boundary conditions. And we say they're boundary conditions because we're going to have one of them specified at one end on the boundary and the other condition specified at the other end on the boundary. So initial condition will be related to time, the time variable, and the boundary conditions will be related to the spatial variable, which I think is consistent with how we think of initial conditions and boundary conditions. So first of all, here are initial conditions, or condition. And we only have one because the PDE is first order with respect to time. And I'll use WRT for with respect to. And of course, we could specify the temperature at any time, but typically we specify the temperature at T equals 0. So we'd have the temperature as a function of X at time T equals 0 is given by some specified function of X for X between 0 and L. So this is giving us the initial temperature of that rod. We might say the initial temperature distribution, because the whole thing is not one temperature. It's a temperature that depends on X, depends on where you are in the rod. Okay, that's our initial condition. Now for the boundary conditions, you've got two boundaries. You've got one at X equals 0 and another one at X equals L. Now, there are many types of boundary conditions that we could specify, but we're going to talk about those that are physically meaningful. And since it's a second order with respect to the spatial variable X, we expect two boundary conditions, or we need two boundary conditions in order to describe that temperature in the rod without any constants in it. Now, there are four main types of physically meaningful boundary conditions. And we'll outline all four of those. To simplify our discussion, I'll use the same terminology that Dr. Constanda used in his textbook. If this is our rod and it has a length L, this endpoint at X equals 0, we're going to call the near endpoint. And I'll abbreviate that end PT for point. And I guess it's a near endpoint if you're sort of standing over here. If you're standing over here, the one on the other side at x equals L would be the far endpoint. Okay. So with that in mind, let's talk about the four types of physically meaningful boundary conditions. The first is that the temperature might be given to you. And of course, we're talking about given to you at one of these endpoints. So you might be told that at x equals 0, the temperature is given to be some function of T for all T greater than 0. Or you might be told that at x equals L, the far end point, the temperature is given by some function of T. But this is just specifying the temperature at that endpoint. So let's write that down. This one specifies the temperature at x equals 0. This one specifies the temperature at x equals L. Okay, so that might be given. Now, it may also tell you that one of the endpoints is insulated. Now, for our purposes, that's equivalent to saying that the heat flux at that endpoint is 0. And of course, heat flux is proportional to that partial derivative of the temperature with respect to x. If there's no heat flux, because the rod is insulated, let's say it's insulated at x equals 0 at the near endpoint. Whoops, then we would have this. And I really want you to keep this visual in mind. There's an actual rod there. We're talking about it being insulated over here at x equals 0. Or maybe it's insulated at x equals L at the other side, or on the other side. So at x equals L, for all time, there's no heat flux. Okay, so that's possible. Now it's also possible that they tell you what the heat flux is. Dr. Constanda actually combines these two, but I think that they ought to be addressed separately. In that case, that partial derivative of temperature with respect to that spatial variable, so we're saying how is the temperature changing as x changes, at the near endpoint, it might be given to be some function of t for t greater than 0. Or we might be given the flux at x equals L. It can be very similar. This is the rate of change of the temperature with respect to our spatial variable at x equals L for all time that we're interested in is given by this function. Okay, so one of those would be given. Now, the fourth possibility is that one of the endpoints may be in contact with another medium. In that case, we apply Newton's law of cooling. And you guys probably remember Newton's law of cooling from other classes. But of course, your ordinary differential equations class probably covered this as an application of first order differential equations. Newton's law of cooling says the following. The heat flux at an endpoint is proportional to the difference between the temperature of the rod and the temperature of the external medium. So heat flux, remember, was thermal conductivity, which we're assuming to be constant. We're assuming that rod is uniform, times the partial derivative of our temperature with respect to our spatial variable x. If the heat flux is specified at x equals 0, that's how we would represent it. So that's change in temp with respect to x, holding t constant, but we're interested in that change in temp with respect to x holding t constant at a particular x value, saying at x equals 0. What does that flux look like as a function of time? And that's, again, heat flux, which is heat energy per unit area per unit time. Newton's law of cooling says that that is proportional to the difference between the temperature of the rod, and we're assuming this is at that near endpoint at x equals 0. So there it is. And we're imagining we're standing here. It's next to us, so we call it the near endpoint. Temperature at x equals 0 as a function of time, minus the temperature of the external medium, which may actually depend on time. And of course, we assume that this is known. And this constant of proportionality H is greater than 0. It's called the heat transfer coefficient. And remember the situation we're looking at. It's describing the heat flux at x equals 0 as a function of time, provided that that end is in an external medium with this temperature. Okay, now remember when we discussed the heat flux, which was given by this function, we said we're going to choose going to the right to be the positive direction for heat flux. If heat is flowing that way, we're going to call it positive. If it's going the other way, we're going to call it negative. So that means when we talk about the heat flux at this endpoint, it's going to have the wrong sign. It's going to be going to the right. if we're interested in heat going in, like we have to multiply it by -1. So on the other side, it would look like this. The heat flux would be -1 times that thermal conductivity times the partial derivative of u with respect to x at x equals L. So on the right endpoint, at that far endpoint, we're over here. I almost imagine looking through binoculars and looking at the other endpoint. It's far away. X equals L as a function of time. This is heat flux is equal to that heat transfer coefficient times the difference between the temperature at x equals L as a function of time. So we're over here and we're talking about this minus the temperature of the known external medium, or the known temperature of the external medium, excuse me. So this is the constant of proportionality. It's a change in temp, or this says the heat flux at an endpoint, Newton's law of cooling says that, is proportional to the difference between the temperature of the rod and the temperature of the external medium. We're saying all of that is true at x equals L. Or here we're saying all of that is true at x equals 0. And then because of this convention, we multiply this by -1 at the right endpoint. And all of these little labels I've written here also apply down here. Okay, so those are our boundary conditions. So maybe you know this. You know that the far endpoint is in contact with an external medium with a known temperature given by U of T. Then you would use this. Or maybe you know that not about the far endpoint, but the near endpoint. Then you would use this one. Or maybe you know what the heat flux is exactly at one of those endpoints. Then you would use this one or this one. Or maybe somebody tells you it's insulated over there. Then you would use this one or this one. Of course, depending on what side of the rod you're talking about. They've got to specify. And then, of course, they could just tell us the temperature at x equals 0 or x equals L. So those are the possible boundary conditions. This is our initial condition. Before we come up with a mathematical model, which will be described more fully in the next video, there are a couple of notes from the book that I thought were worth pointing out. We're only going to prescribe one boundary condition at each endpoint. Now I know it's second order with respect to x. Some students might say, well, can't I just, maybe I can talk about what happens at x equals 0 and maybe talk about flux at x equals 0 or something else. No, you want one boundary condition at x equals 0 and one boundary condition at x equals L. And that will allow us to find that u of x and t, that temperature function that we're looking for. Of course, I think it's sort of obvious that the boundary condition at x equals 0 may be different from the boundary condition at x equals L. Like, of course, that's true. Maybe one end is insulated and the other one, on the other end, the flux, or maybe one end, somebody gives you the temperature, and at the other end, they say this end is in an external medium, and that external medium has this known temperature. So, I mean, there's absolutely no reason that this endpoint needs to be treated exactly the same as that endpoint. So that's fine. I think if you know about linearity and what it means for a differential equation to be linear, I think you can look at these differential equations. I think they're obviously linear. Excuse me, where did that differential equation go? Yes, this fits the form of a linear differential equation. You could also just substitute in a constant times u1 plus a constant times u2 and show that if u1 and u2 both satisfy the differential equation, well, it will have those properties of linear operators that we're familiar with. And Finally, this is the simplest example of what's called a parabolic equation. And that is an entire class of second order linear partial differential equations. So parabolic second order linear partial differential equations have certain solution methods that apply to them. Understanding the heat equation is a really good first step to being able to generalize to other parabolic equations. We'll talk about that when we get to chapter 11 in the book. But first, we'll talk about three different methods for handling the heat equation subject to some boundary conditions and an initial condition. In the next video, we'll put the differential equation together with the boundary conditions and initial conditions to come up with that mathematical model, which we'll call an initial boundary value problem. And then we'll discuss the solution of that model and existence and uniqueness in questions like that. So that's it for this video. It's our derivation of the heat equation. If you want to learn more about the heat equation, come back for the next video when we'll talk more about that model and its solution.